Good morning, everyone. I'd like to welcome everyone and thank you for taking the time to join the DeZURIK RCV presentation. So today we're going to talk about the DeZURIK RCV, an overview of the product. We'll do a competitive comparison, a hands-on. We'll talk a little bit about our trims and our steam trim. And throughout the presentation, we will talk about specific selling points for the DeZURIK RCV. So what is a rotary eccentric control valve? The RCV is that valve. It's also referred to as a rotary globe valve as well. The RCV provides a high CV, a wide range of service conditions, multiple types of media from clean fluids to abrasive slurries, provides excellent control, ease of maintenance, and due to the high cost of larger globe valves, we offer a competitive advantage in typically 3-inch and larger sizes. The exception to that would be valves on slurry service where globe valves are typically not effective. So smaller than 3-inch slurry valves, an RCV or rotary control valve is typically the valve of choice for these applications. So when we say an rotary eccentric plug, what are we talking about? If you look at the top picture, you'll see that the plug is in the closed position with the seat. As in the middle picture, as the valve starts to move when it comes off the seat, there's no contact between the plug and the seat. That's due to the eccentric motion of the plug. It pulls away from the seat. And then the bottom picture, you'll notice that we have a very clear, unobstructed, straight through flow path. Typically we have less wear and tear from abrasive surfaces and media onto the plug and the seat. One of the key differentiating features of the DeZURIK RCV is our seat design and more specifically our seat retainer. As you can see, we use a drop-in seat retainer. This, along with the orbital seat design, allows the plug and the seat correct alignment. But with the drop-in seat retainer, we have no threads, no internal body threads, whereas most of our competitors have a threaded seat retainer. It makes the valve much easier to assemble and disassemble. Our trim is essentially a drop-in place trim. So it's dropped in place, the seat retainer is dropped on top. And when the seat retainer is compressed by the flanges, it actually bottoms out in the body bore, which provides the correct plug to seat contact or plug to seat loading. The other important feature is no special tools are required to remove our seat retainer for assembly and disassembly. We have 4 seat options or 4 CV options with each valve size. All of our trims or our seats are interchangeable without changing the plug. This is true for our competitors within certain size ranges, but there are also size ranges where if they change the trim size or seat size, then they also have to change the plug. We don't have to do that. One thing I want to point out is the common sealing surface. If you, hopefully you can see my pointer, but the sealing surface is in the same place on all of our trims, regardless of the CV, and is on the outboard side of the trim. So the top picture is a high trim, a large hole, large CV. The bottom picture is a reduced port or reduced CV, but you'll notice the sealing surface is in the same place. This becomes very important in abrasive services because, as you notice, you have a lot of material that can wear away before you will get into the seating area of the valve. We also offer hardened overlays, primarily tungsten carbide, on the seats to give us some additional protection against erosion and extend valve life. If required, we can also do some anti-stick coatings with Nidox, which will help us in scaling slurry services to help prevent scale or buildup from occurring on the seat. We mentioned before the 4 trim sizes. This chart gives you a comparison of our CVs. You'll see that we have what we call high capacity trim, full capacity, 0.5 reduced, and 0.2 reduced capacity trims. In the column on the right, this is a CV, comparable CV or max CV of most of our competitors. So what you'll see is that lines up with our our full capacity trim. And then we have another option for a higher CV or more capacity in a given valve size. So most of our competitors have three options on trim sizes. We have 4. It gives us more options when we're sizing the valve, and sometimes will allow us to use a smaller valve than our competition in a given application. Okay. We mentioned our orbital seat. This is the key, one of the keys to our valve. One of the things you'll notice in the picture on the left, the center line of the valve, the center line of the valve, for us, we use a concentric valve body, which means our valve shaft goes right through the center of the body. It's not offset. So we had to come up with a way to give us the eccentric motion that we needed for this valve in a concentric body. The way we accomplished that was with the orbital seat design, and you'll notice that the way the seat sits at a little bit of an angle in the seat retainer, we actually machine an ellipse into our seat retainer, which gives us the proper angle, and we then over-rotate the plug just a little bit, and that allows us to get that eccentric motion. So when the plug starts to open off the seat, it pulls away from the seat, so we have no contact other than when the valve is going fully closed. Our shaft design is a little unique to us as well. We use a split shaft. The split shaft gives us a high flow capacity. We use a spline connection. It's a 24-2 spline that connects the plug to the shaft. And then we also have a set screw that loads the spline against itself. This gives us a zero backlash or zero hysteresis between that connection between the plug and the shaft. It also provides us blowout proof protection. The set screw, once it's put in, it is staked so it can't back out. Not having the open area behind the plug, not having the shaft that runs all the way through, also gives us less turbulence in the higher velocity areas, which is important when you have abrasive medias going through the valve. Standard shaft materials are 2205 duplex. We have many other shaft materials available as well. We also use a square drive on the top of the shaft for our connection to our actuators. All DeZURIK actuators are direct mounted to the RCV. And then with our collet design on our power rack or our clevis design on the diaphragms, it gives us once again, a very solid hysteresis free connection to where we have zero backlash between that shaft connection all the way from the plug up through the actuator. The other thing that's important, and this once again gets back to the 2-piece shaft, as you see, we have a straight through, a clear unobstructed flow path. As we mentioned, that's less turbulence than what you would have if you had a shaft that goes all the way through the valve. We also provide 90 degrees of stroke on our RCV. Our competitors are going to be 60 to 75% rotation. Being able to control over the full 90 degrees gives us a higher resolution and better control with the RCV. The picture on the left is a 6-inch RCV with our high capacity trim, and the picture on the right is the same 6-inch RCV with our reduced 0.5 reduced trim. For our seat retainer and seat retainer seals, we have 3 seal options. The seat retainer seal is, if you can see my mouse, is the seal here, and that is actually the seal between the seat and the retainer. It serves really 2 purposes. Number one, it prevents leakage around the seat. And the second function is it allows our orbital seat to work. So we get a slight bit of movement between the plug and the seat every time the valve closes. That gives us the alignment that we need with every stroke to shut off. The first option, the standard, is a Teflon encapsulated Viton O-ring, essentially a groove in the seat retainer where the O-ring is retained. This is bidirectional in service, so flow can go either into the face of the plug or behind the plug. The temperature limit is 500 degrees F. Our second option is an Inconel C-ring, which is once again a groove in the seat retainer, and we have an Inconel ring. This is a unidirectional seat, so we only can put this valve in the flow to open position, which would be flow into the face of the plug or flow with the shaft downstream. The temperature limitation on that design is 1,000 degrees F. The third option is what we refer to as our steam trim, which is a graphite seal. In the picture on the bottom, you'll see the standard trim that we just showed. The picture on the top is the steam trim. So essentially, we modify the seat retainer. We have a couple of graphite rings that are here, and then we have a piece that helps load those rings when the seat retainer is put into the valve. This valve will be installed in the flow to close position, which is flow into the back of the plug. The reason that's important in steam service or any really abrasive service is your high velocity area going through the valve is going to be the area going through the seat. And these are typically going to be modulating valves. So that allows us to direct that high velocity flow into the seat of the valve and into the center of the pipeline, versus the flow was going in the other direction. The flow would impede the plug and be directed into the body of the valve, and can where the premature failure of the body, essentially you can blow the side of the valve out. It also allows us to provide, when we provide a hardened trim, so we can put tungsten carbide over the seat. So now we're directing that high velocity or abrasive flow into a hardened trim, which is also obviously repairable. This arrangement is bidirectional, so it could be installed in the other direction if a situation warranted it, but typically it's going to be what we call our flow to close orientation, and the temperature limitation for this valve is 800, or this seal is 800 degrees F. Our bearings, which you'll get more appreciation for in the hands-on, but we use solid bearings, both on the top and the bottom. Standard bearing material is 440C. We also do these out of stellite, solid stellite or alloys. One important feature about our bearings, you'll notice the O-ring grooves. In the picture on the left, this is the seal or the groove on the outside of the bearing. If you look at the picture of the right, you'll see the seal on top, and you'll see the bottom ring as well. That's on the ID of the bearing, and these are for what we call bearing seals. Typical materials are Viton or Calres. Bearing seals are an option that should be used when you're dealing with a slurry service or anything where you could have material that could plate out in the bearing areas. Because of the tight tolerances on any bearing system, it doesn't take a whole lot of material to build up in a bearing area to lock down a valve. Bearing seals will give us the option to extend the life of the valve by helping to keep material from getting into the bearing areas and building up. Installation. We mentioned a little bit about flow to close and flow to open. Flow to close is essentially flow coming into the backside of the plug or with the shaft upstream. As we mentioned, it directs the high velocity flow into the seat, which can be a hardened seat as well. It also directs it into the center of the pipe. One other option that is typical for any type of rotary valve is if you're mounting the valve in a horizontal pipeline, it's always good to mount the shaft horizontally as well, with the plug opening up towards the top of the pipeline. And what this does is it eliminates or helps keep material from just settling in the bottom of the valve around that bottom journal area. As when the valve's operating, it keeps, it'll stay flushed out. We recommend the flow to close installation for any service where we might have flashing or cavitation, certainly on steam service, and it's a must on slurries. Flow to open is the shaft downstream. So you see flows going into the face of the plug, the shaft is downstream. This is typical for clean fluids, air, gases, things like that. And we'll start the hands-on.
We'll start out by looking at the valves here, at the bodies. Here on the left, we have the Mason-Elin Camflex. In the middle, we have the Fisher V500. And we have on the right, the rotary control valve, the RCV. All three are one-piece sand castings. We'll take a look at some of the difference between the bodies. If we look at the Camflex, the back side of the flanges have been machined. Looking at the Fisher and the RCV, the back side of the flanges are still raw cast surface. Just a visual difference, nothing functional there. The RCV body, actually let's look at another thing too, is the holes on the flanges. Notice that the V500 has more holes than what we see on the Camflex and the RCV. So we have, these are the class 150, the Camflex and RCV, and in the middle we have a class 300. And the class 300 has the same internal components as what it would for a class 150, and the same would be true for any of these products. So since they're the same, we'll still have a good visual comparison of the size and the shape and everything. It's the same components regardless whether it's class 150 or 300. Looking at the bottom of the body, we'll start with the RCV, and you see the lower cover. This is the casting is machined, and we add the lower cover with the screws for retention. That allows access for the shaft. We can bring our lower shaft in from the bottom. Looking at the V500, there's no shaft access whatsoever, although there is an available option to put a plug in there. Being that the V500 has a one-piece shaft and it comes in from the top, the plug on the bottom, when it's ordered, does not allow the shaft to pass through. And looking at the Camflex, it also has no access in the bottom. So with the RCV, it's a standard feature to have the lower cover, and it's an available option on the V500 and not with the Camflex. Looking at the neck length, the RCV has a shorter neck compared to the V500 and the Camflex. The RCV allows for 2 inches of pipe insulation, and that's measured from the top of the flange to the body wall. That's as standard. And on the V500, it allows for 4 inches as well as the Camflex. They allow 4 inches of pipe insulation from the body wall to the top of the flange. The Camflex has a unique feature compared to the other products. It has this retainer screw. And looking at the shaft, there's a hole in this collar that the screw retains. So they call it a retainer screw, and that's used for locating the plug. And they have this sleeve for stack up. This could also be an additional leak path to the atmosphere. It does provide for secondary blow-proof protection as well. For actuator mounting, the RCV has 4 holes in the top flange. The V500 uses 2 mounting holes. The Camflex uses these 2 mounting screws, and these are actually for the gland. The Camflex uses these 2 mounting screws for the actuator, and these are the gland studs. For flow direction, looking at the Camflex, there's a tag that's riveted on in the top flange. The V500 has it cast in. In the RCV, a tag is an available option, more in the likeness of the Camflex, it'd be a riveted tag.
One thing that when you notice the shorter necks, I think I mentioned it before, but I'll reiterate that our RCV body is the exact same body as our VPV body. So that's one of the design reasons why we have a little bit shorter neck on ours. Typically, we have not had in the past pushback as far as insulation length. Our mounting stool that goes on top, we have these valves installed where they have up to 4 inches of insulation. So it's not been an impediment to us to date.
Now let's take a look at the shafts. Bring them up here to the shelf where we can get a little bit closer look. There's the RCV and the V500 and the CamFlex on the left. The V500 and the CamFlex are both single one-piece shafts. The RCV has a two-piece shaft. And with that two-piece shaft, there's more available flow capacity. Now, looking down the valve or down the pipe through the valve, you would have the shaft in the way of the flow. So on the CamFlex and on the V500, but the RCV, that's a clear open flow path. So that gives us more capacity. And with that, we have more operating range. The RCV has a full 90 degrees of operating range for the plug and stem rotation. And because of that, it will sometimes allow use of a smaller valve than our competition, which you size it up in alpha 1 and check, but you could potentially save some money on the larger sizes above 3 inch. You could possibly offer a smaller size valve, because when we size valves, we don't always use a line size valve. So like for a 6-inch pipeline, perhaps you use a 4-inch valve, depending on the flow capacity that you need. The V500 and CamFlex both have spline shafts for actuator connection. The RCV has a square shaft. Our power rack and diaphragm actuators are direct mounted and offer a solid shaft to actuator connection with no measurable hysteresis when combined with the 24-tooth spline connection. Let's show that 24-tooth spline. And looking down the So once this screw, this is a torque screw, once it's applied and full assembled, it makes this whole assembly for the shaft and the plug all as if it were one solid piece. It's very tight and there's no measurable hysteresis. Stack up on the valve, stack up of the whole assembly, the shaft and the plug and so forth is controlled by the bottom journal for the CamFlex and for the V500. But for the RCV, the stack up, which controls the center of the plug and its location to the seat, that's controlled by the bottom cover. So looking again at the RCV body, this machine surface on the body, the lower cover comes up against it. Then all the force from the gland studs going through the packing, down into the washer and into the plug and all the way down into the lower shaft, that's all compressed all the way starting from up at the top of the gland studs. That means that there's no play and everything is tightly controlled by the machine surface on the bottom. It's very tightly located. That keeps the plug from floating in respect to the seat and keeps it well located. We believe this is a better design because it's not subject to machining tolerances in the lower journal area in the way that the competitor products are.
When we first started and developed the RCV, it actually had a 16-tooth spline. And this was in the early days of Intech and valve performance testing. And one of the things we found that even with the 16-tooth spline, we had more backlash than we would have liked. So I think somewhere around 96, 95, 96, we made the change and went to the 24-tooth spline to increase the performance of the valve and eliminate any of that potential hysteresis in that connection.
Now let's take a look at the bearings. The RCV has a lot more bearing area than the competitor products, and the functional bearing area is really more about where the shaft is in contact with the bearing than it is bearing with the outside of the body. There's higher stresses on the inside diameter. So let's focus on the shaft diameter and the length. When we look at the RCV, I'm going to kind of bring these closer to the center of the camera for better viewing. When we look at the RCV, you have a lot of length compared to the length of this bearing for the V500. or for the CamFlex, shorter bearings. The diameter on the inside of the RCV bearing, the shaft diameter is about the same as a Fisher. So right there, having extra length, the RCV has more bearing area to spread out the stresses. Looking at the CamFlex, look at that teeny little shaft diameter on the bottom, and the bearing inside diameter is very small and very short. So there's not a lot of bearing area here that's higher stress in that lower journal. When you install these valves, you always want to install stem horizontal when possible, because that keeps grit from getting down here in the first place. And having additional surface area spreads out the forces, reducing stresses, thereby reducing wear, and promotes longer service life compared to the V500 and the CamFlex. The RCV bearings have O-ring grooves on the outside and inside. It's pretty hard to show on the camera, the inside groove, but I think we saw it from the slides pretty well, that there's 2 O-ring grooves on each bearing, one on the outside, one on the inside, and they're offset. That helps to keep the grit out from the bearings, is better for slurries and any media with solids. It allows for the bearings to seal good on slurry service. It helps to prevent buildup in the bearing area. And the CamFlex and V500 also offer bearing seals as available options. CamFlex use a sleeve to locate the lower bearing, and this is that sleeve here. All right, let's move on to the packing. Now, we had some surprises, and by the way, this is kind of a fun project. It's kind of almost like an Easter basket when these boxes show up and you start tearing down these valves and see what's inside of them. A lot more color than when you're looking at like an instruction manual, for example. But when we started to tear down these valves, we had some surprises. And looking at the packing, you know, there's some similarities in the packing system, and there's some pretty significant differences. RCV uses the PTFE V-ring packing as standard. And all 3 products have graphite for higher temp service as an available option. But as a standard, the PTFE V-ring packing and the Fisher had graphite packing in it, which probably would have been destroyed if we tried to remove it, so we left it inside the valve. And then the CamFlex actually has braided PTFE packing with the carbon core. Similarity in the systems between RCV and the V500 is they both have a 1-piece gland, and essentially the whole packing system is the same concept and similar materials. It's basically, you know, very much the same. You get to the CamFlex, that was one of the interesting surprises. First of all, that the way they do their gland studs, that you have 4 studs in the top of the valve body and a 2-piece gland versus RCV and V500 have a 1-piece gland. So that 2-piece gland, let's get a little better look at it. We get that apart here. It has a O-ring groove, dual O-ring grooves on the outside and dual O-ring grooves on the inside as a secondary seal. So we have the 2-piece gland versus the 1-piece, and we have secondary O-ring seals added. And here I'm getting dirty already because this whole area was kind of slathered up with anti-seize or never seize compound. When we pulled it out, the white PTFE was just all gooped up and dark, and it was interesting they had lubricated it in that way.
This is typical of what you'll see in globe valves and other valves. But you can think of this ring as a landing area for the packing. It serves a couple purposes. It gives the packing a solid landing ring, so when it's compressed, it compresses evenly on both the ID, which will be on the shaft, and the OD, which will be the body wall. Also very important when we're using Teflon packing, because it's a pretty, the tolerances are pretty tight on the fit to the shaft, so it helps eliminate potential cold flow of the Teflon packing.
And we don't see this washer on the V500 because on the V500 it's still buried in the valve below the packing. Otherwise we would see a similar piece on the V500. Yeah. Okay, moving on to the plugs. The RCV plug is much larger than the V500 and the CamFlex. let's take these off and set them side by side, and you'll see how much of a difference this really is. Let's take a look at the pinning as well. So I'm putting the cam flex in the middle to make it more apparent how small that cam flex is compared to the RCV. I'll try and bring them up here once too, a little closer to the camera. So the one on the top of your screen, that's the RCV. And it has about twice the, the area on the plug face is what the cam flex has. And it's about 50% larger diameter. And then you have the V500 plug, this one. And it's about 25% smaller than the RCV. So visually and functionally, there's some differences I'll get into in a minute in terms of function, but mostly it's just kind of interesting to note from a visual perspective. The RCV plug and shaft have a tight spline connection. So here we see that 24-tooth spline. See if I can get a good angle on it. There we go. And on the right, here's that torque screw right here. And that mates up with the dimple that's drilled into the shaft. Now, once we tighten up the torque screw, this connection becomes very tight, extremely tight, as if it was one solid piece. There's no hysteresis. It also provides secondary blowout-proof protection. And we stake this, once the torque screw is screwed all the way in, then we stake it for retention so it can't come back out. It actually deforms the threads. The cam flex has an interesting connection, significantly different. It's a 4-flute spline. We can get a good view looking straight down. There's 4 flutes on the shaft. Hopefully y'all can see this really good remotely. And one thing that was noteworthy is just handling these parts. Since I'm actually able to do so here, I can feel that there's a little bit of wobble in here. And that wobble between the plug and the shaft, that's actually part of the design concept for sealing, which allows the plug to float just a little bit as it comes into the seat to help get that full contact. V500 plug and shaft have a pinned connection. This is the V500 plug. And the shaft has a hole straight through, which puts this pin and sleeve in shear. And what's inside this pin, it was interesting to take apart because on the back side, this little knob, the little tip of that pin sticks out. You just tap it with a hammer. But when I say tap, yeah, actually I had to take a big punch and really wind up on it, which was a little bit scary because my hands were holding that punch. But once it finally came out, we got a good look at it. What it is, it's a 2-piece system with a taper pin on the inside and a straight cylinder on the outside. And the taper on the inside is a locking taper. And there's no secondary retention for this pin. It's just a locking taper. Once they set it, they have to pound on it really hard to get it in there and to get it to stay, but then there's nothing secondary that keeps it in place, keeps it from coming out. The plug and stem rotation is different on one of the 3. So looking at the RCV, I'm going to put these back together quick. Looking at the RCV, we have clockwise to open rotation. So plug stem opens by rotating clockwise, or counterclockwise, and then clockwise to close. Excuse me. So it's counterclockwise to open, clockwise to close. And the V500 is the same in that regard. It's clockwise to close, counterclockwise to open. I got this on backwards. The CamFlex is the other way. So if I put it side by side with the RCV, it's actually clockwise to open, counterclockwise to close. And the offset in the plug is the opposite direction. So this more demonstrates the offset, where the plug face on the RCV, looking from the bottom of the valve, is off to the right, and the V500 is off to the right, and the CamFlex is off to the other side. Also looking at the plugs, notice this clear area where the flow is. Fisher has a little bit of a gap to allow additional capacity between the shaft and the plug face. And then the CamFlex has the arm that's in the flow path. Now, the name CamFlex comes from this arm. This is the CamFlex plug. And you've got the shaft hole, you have the arm and the face. And it's this arm that actually flexes from the torque provided by the actuator. It flexes when it makes contact with the seat. In addition to the wobble on the shaft and with the flexing of this arm, that's how they achieve their seal, because the seat and the seat retainer connected to the body is a completely rigid arrangement. There's no play or float or resilient members of any kind. It's a very hard, rigid stack up in the body and seat and retainer. So the way they achieve their seal is by having a plug on the shaft being just a little loose so it can get that last couple thousandths of positioning, and then also the flex of this arm right here. And that's what this arm, that's where we get the name CamFlex. The Fisher has, and we'll get into the retainer and the flexibility of the Fisher seat in a moment, but the operating range for the RCV is 90 degrees because of the wide flow area behind the plug. And then because we have the shaft in the stream for the V500 and for the CamFlex, those have less operating range. They're only, and say for the Fisher, the particular valve we have here is 76 degrees operating range, and the CamFlex only has 60 degrees of operating range. And so the RCV having a wider operating range, meaning how far you can rotate the plug, the RCV is a full 90 degrees, while the others are less. That gives us more 200 discrete positions compared to, say, 150 discrete positions. So it gives us more control resolution. That last 30 degrees of rotation for the Fisher or for the CamFlex do not increase the flow capacity of the valve anymore. So as you come from full closed and you work your way through the operating range closer to full open, well, full open on the CamFlex will be 60 degrees. After it rotates beyond that, there's no more flow capacity, and that's as much as the valve, you've reached capacity and you can keep opening it, but it doesn't do anything. So we have greater control resolution and greater operating range.
The comments about the clear flow through the RCV, if we're dealing with an abrasive, erosive slurry, we're going to have that erosive material or media acting more on our seat, which can be hardened. You can see that you'll create a fair amount of turbulence with the other two designs and have potential for wear on the plug member and the shaft as well, where we don't have that with the clear flow path through the valve.
We'll take just a moment to get these components back laid out, and then we'll get into the shaft and seat retainers, or get into the seat retainers and the seats.
One other thing, if you'll pick up the RCV shaft and show the very top of the shaft.
Okay.
I don't know if everybody can see there's a line scribed across the top of the shaft. That line indicates the plug position in the valve. So if you ever have an actuator off a valve and the valve's in line and you need to know the plug position, that line scribed across the top will indicate the plug position in the valve.
All right, let's take a look at the seat retainers. Here are the Camflex. We'll take them out one at a time. Camflex has a threaded seat retainer. And here's the seat. Here's the V500 seat retainer. Here is the seat with the seal rings. And now, is the RCV. So some things should be very apparent already, and I'll try to put some words to it. So let's start out with the RCV, which is truly a drop-in seat retainer. When you say truly drop-in, consider that there's no special tools like a spanner wrench. Notice the slots in the seat retainer on the other products. There's no spanner wrench or any special tools required to remove our seat retainer. There's just two socket hex cap screws. There's no worries of galling the threads on these retainers, which is a big problem for maintenance. There's no gaps to set with a feeler gauge. There's no torque charts to follow when you're turning the seat retainer in. You don't have to follow any torque charts. For the V500, it wasn't very easy to remove. There's a little bit of deformation where we were pounding on it with a punch and a hammer. And then the Camflex, even though it's smaller, was even worse. We had to use heat to remove it, used a propane torch.
All three of these products are well-known products. They all have a good reputation and they all work. They all work in tough applications. And because of the applications that these valves are put in, they are going to be a maintenance item. And if you've ever had to try to take apart a Camflex, the predecessor to the RCV, which was called the K-Max or V500, the issues are largely deal with getting the seat retainer out. Number one, you're typically dealing with a stainless retainer and a stainless body. Stainless on stainless is not a good combination. It's always going to gall or have the potential for galling. If you're in a process where you're going to get material, you are going to get material back up into those threads, which further complicates being able to get this valve apart. And you have to have a special tool or a spanner wrench, or it's time consuming and very difficult to get apart sometimes. And then you've got to clean it up to be able to get it back together. This is probably the most important point on the or feature of the RCV is the drop-in retainer. It's essentially drop and go. There's no shims, there's no filler gauges required, there's no spacing required. Everything is loaded up when this valve is compressed between the flanges. So in our design, without the threads, it's very simple to pull apart. It's a simple valve to maintain, to rebuild. And one important note, when the seat retainer everything's dropped in the valve, we have these two hex head retaining screws. Those two hex head retaining screws are not there to load the seat retainer to the valve body. They're there to keep everything in place. When this valve is flanged up in the line, that's what's going to truly load in the seat to the plug. So it's perfectly okay if those screws are snugged down, but you don't ever have to really tighten up those screws. They're just to retain the parts until this is flanged up in line. We have, as we noted before, the seat retainer actually bottoms out onto the body. So We don't have, as long as they use their normal, for whatever gasket they're using, use their normal torque specs for their bolts, it's going to load our valve properly.
Let's take a look at that ellipse that you mentioned on the RCV seat retainer. I'm going to do my best to hold this in a way that it can see it. There it is. So you see the central kind of uncentered port hole through it, and then you see the angled surface is the really bright shiny surface in the middle. That's the clearance surface. The top of the seat itself goes up in near that. It just makes room for it. But it just demonstrates our orbital seat and the offset and the eccentricity and so forth.
Can you show the witness mark? This is the one critical piece when assembling an RCV, is because of the ellipse that's cut in our orbital seat design, the seat retainer only goes on one way. So there, within the recessed area for the retainer screw, there is a witness mark. It's going to be hard to see on the camera, but there's a witness mark, and that goes up towards the top of the valve. So that always tells you the correct orientation of the seat retainer.
So I just brought my hand up to force an autofocus and get it to come in and focus on that scallop. And right now you can see that dimple. It's the bright little spot in the middle of the scallop where it's dark. Right there.
Yeah.
So there's two scallops. Well, there's two screws on the body, two retainer screws. And one of the scallops doesn't have the dimple. This one actually does have that witness mark tapped into with a punch. Okay. Taking a look at the V500, the Fisher seat. It has two seals on it. When the valve closes, these metal seals, and hopefully you can get a good look, see how they look kind of like they're an accordion style? They're hollow, they're not solid. They're just formed sheet metal. Now when the valve closes and the plug comes in contact with the seat sealing surface, that's going to load up the seal on the far side. And as that seal loads up, there's some deflection there until such time that the plug comes and makes full 100% contact on the full circle. So it's essentially spring loaded. For the sizes 2 through 8 inch, there's a gap required between the seat and the plug, which is measured by feeler gauges during assembly to obtain the correct seat loading on the plug. Looking at the CamFlex seat, as I mentioned earlier, it's a rigid seat and retainer. When we put these into the body, there's nothing that has any give whatsoever. It is tight. The sealing surface, which is right here. Show a little closer. When these go into the body, it's very tight. There's no room whatsoever. It's located by the threads in the shoulder, and the sealing surface cannot move at all. So again, that's where the flex from the plug comes into play. They need that arm to flex, and they need a little bit of gap between the plug and the shaft, and those little bits of motion of that plug face allow it to come into full contact with the seat. Also, the mass of the seat is an interesting and important thing to point out. Notice the mass, difference in mass between these parts. There is a lot of material in the RCV seat and retainer. There's not very much material in the CamFlex, and the Fisher is much more in likeness of the CamFlex. They're similar size. Fisher's a little heavier, but the DeZURIK is very rugged, very robust, very heavy. And when it comes to erosion, having more material is better. So something to be aware that we do have so much more mass in our seat and our retainer and more robust parts. One final note on plugs and seats was the lubrication. And both of the threaded retainers were all lathered up with probably a copper or nickel-based, metal-based non-stick anti-seize. And the RCV, the only place that we're doing that is on our retainer screws, which are outside the flow path. And these parts were actually quite dirty when we took them apart.
One of the key features for us, these valves are typically installed in services where they are going to be abused and they have to be rebuilt and maintained. So if we take away nothing else from this presentation, it would be the ease of maintenance on the RCV. That is, I think, our most distinguishing feature that we have in our valve design versus our competitors.
Okay, good. I'm going to just demonstrate reassembling, putting these retainers and seats back in the valve. Here's the RCV seat. Again, the sealing surface is, see if we get a good angle to the camera to show it. There we go. This angled surface, which just happens to be tangent to the full flow path. And smaller seats will have a little bit more material in the middle, which is not sealing surface. So I actually have one right here to point out. If we use a 0.5 reduced trim, the sealing surface is this ring near the outside. All this other material, that's everything closer to the center from my fingernail, is all just clearance. All that is doing is restricting the orifice. The actual sealing surface is all the way around the perimeter, this angled surface right here. Okay? So, an important feature is a drop-in seat. When the plug is in the body, you drop the seat in, you rotate the plug up just a little bit so that the plug comes up just a little bit off the body. Check the witness mark. Here we have the witness mark. Now we're going to put that toward the top and just drop it in. Put our 2 screws in. All that does is hold it in place. When the valve gets flanged in the pipeline, that's going to compress everything together as it needs to be. Now for the V500, we'll put in the ring, the seat, the second ring, and the seat retainer. Get out your spanner wrench. Hopefully you have one. And then for the cam flex, the seat, and the seat retainer, torque them to spec, go to lunch.
So selling the RCV, what we're looking for are large control valve applications. 3 through 12 inch are ideal, where we have a competitive advantage against globe valves, or as we mentioned before, smaller sizes certainly in slurry service. One of the things to be aware of whenever we size a rotary valve is high noise or cavitation. For steam service, RCV is an excellent steam control valve as long as the differential pressure and noise are reasonable. If we're dealing with a very high DP steam application, that's typically going to push people into a globe valve because there's going to be some noise attenuation trim that's required, which we don't offer in the RCV. So we mentioned slurry applications, flow to close installation. Hardened trim is certainly an option that we would look at on erosive slurries. And some of the points to focus on with the RCV are the high capacity or CV, ease of maintenance, and our multiple trim options in a given valve size. Some of the selling tools that we have available, I'm sure most of you have seen the 3D printed models, which for somebody that's been doing this a long time, it's a whole lot easier to carry a plastic valve in with metal parts than to carry a 75 or 80 pound valve across a mill or across a plant. We have some pretty nice interactive 3DS or 3D PDFs where you can look at the valve from all angles, look at individual parts, look at the internals. Those are nice tools. PowerPoint presentations, the RCV information on the website, bulletins, the steam service bulletin. Application solutions, we have a few that we have, but I would encourage anybody that has any application solutions where the RCV has been a success for a customer. We would certainly like to hear about those and write them up and be able to post them on the website for all DeZURIK reps to use. Should also note that the 3D CAD files that we have, RCV is a part of that offering. And then the Alpha 1 sizing program, if you haven't downloaded the new version, I would encourage you to do that. The RCV, one of the new features for it, you can select whether shaft is upstream or shaft is downstream, flow to open, flow to close when you're sizing. We've also added cavitation information. So if we do see cavitation, we can look at the severity of the cavitation. There's a tab that will pull that information up. And we've also included control valve gain, which is an important data point, essentially, that's going to indicate how easy this valve is going to be to control or to tune for the end user.